we find 7. 7 is larger than the pivot, so we're fine. We keep moving. 8 is larger than the pivot. It's fine. We keep moving. Now we detect something that R has gone past L. This is just a loop condition. Okay, so we should not be moving anymore. Okay, because it's pointless. It's pointless now because R now is in the left sequence and L now is in the right sequence. Okay, so we just stop moving, and what do we do at the end is to swap the last item with the pivot. So now the last item here, which we know is larger than the pivot, we are going to swap it with the pivot. So pivot now is here, and this large item is here. And as you can see, the final sequence, it has got elements smaller than the pivot to the left side and elements larger than the pivot in the right side. Okay, so this is just partitioning. So this is what we used in the non-in-place version of quicksort. This is what we used to do by comparing the elements one by one. Compare one by one to the pivot, and if it is smaller than the pivot, we copy it in a new array. If it is larger than the pivot, we copy it in another array. Okay? But here we do it differently. We do not get out of the array. We stay inside it. And if an element is not in the right position, it should be in the right-hand side, and it is in the left-hand side, we swap it with an item which is in the right-hand side, but which should be in the left-hand side. Okay, so we keep doing this swapping until we partition inside. Now, after we have reached this stage, where is it? So after we have reached this stage, basically what we have done here is, now the sequence is partitioned. So next time, we are going to call partition over this part, and over this part, like we did in the other quicksort. Okay, so nothing changed. After partitioning, we are going to call quicksort over this part and quicksort as well over this part, like we did when we had pivot here, smaller than pivot, larger than pivot. What we did, we recursively call quicksort here and quicksort here. So we are going to recursively call quicksort here and quicksort here. So this partitioning, this is not the table we have seen is just the partitioning, okay? So that because it is the operation or the routine which is of interest to us, because this is what makes quicksort in place. So as you can see, we do not need an extra array, we do not need extra big O of n time. So that's the in place quicksort algorithm in this specific version where we do not have duplicates of elements to make it easy, and the pivot is not randomized. So this is the code of quicksort, of in-place quicksort, of in-place quicksort. So we have left and right, and we keep moving left as long as we do not detect an anomaly, i.e. an item which is in the left hand side and should be in the right hand side, and we keep moving right as long as we do not detect an anomaly, i.e. an item which is in the right hand side but should be in the left hand side. So we keep doing that, and then we swap the two items after both loops. Basically, these loops, they move the left to the they move the left towards the right, and they move the right towards the left. And the whole thing continues as long as left is still less than or equal to right, as we have seen in the sequence. Once right goes past once left goes past right here, we stop the bigger loop. Okay, so that's the stopping condition. And then when we stop, all we have to do is to swap the last element, which is indexed by left, with the pivot. This is the pivot, because we have chosen the last element to be the pivot. And then we recursively call over the left hand side and over the right hand side, and that's in place quicksort for you. A more wordy version with comments is also available for you to understand it better. So this quicksort does not require extra big O of n space. It only requires big O of log n space because it's a recursive algorithm. So it requires constant space in every recursive call, and because we have this quicksort in the worst case requires big O of n extra space, because remember the recursive call, let's do it again. If you remember the partitioning, if the pivot is not randomized, then the partitioning could be something like that. Right? So this is the worst case. There are n recursive calls. Each one takes big O of 1 extra space, so in total we take big O of n extra space. If we randomize the pivot, then what we get is the sequence. We partition it in place into almost equal half sequences, and then almost equal half sequences. Each recursive call takes big O of 1 extra space, and the depth is log n. So we are going to have big O of log n extra space. Okay? So the quicksort that we have just seen, which uses the pivot, or which chooses the pivot to be the last element, i.e. it is not random, this one has a worst case space complexity of big O of n. If we make the pivot randomized, then it will have extra space of log n with a high probability. It still can go to big O of n, but with a low probability. Okay? So now we can merge everything together. We have an in-place quicksort. We change the pivot to be instead of being the last element, we make it random, and this is the ultimate form of quicksort. So it's in-place randomized quicksort. It's not exactly as the other one, because now the pivot changes places, and because we have to take care of duplicate elements. So I'm letting you figure out how it works. Okay? So this is in-place randomized quicksort. This is a table which is going to summarize everything we have seen in terms of best case, average case, and worst case for both time and space. So quicksort, we have seen quicksort which is not in place and which is not randomized. We have seen quicksort which is not in place but which is randomized. We have seen quicksort which is in place but which is not randomized. And the ultimate form is the in-place randomized quicksort. Okay, so this table is going to basically summarize everything we have seen about the complexity of these algorithms. The stars here are explained in the next page. Okay, so you should be able to explain any of these values. So if you are asked why is it big O of n here, you should be able to explain exactly why. Okay, because we have seen all that. This is a summary. Space requirements. Combining sorting algorithms. This is the last thing we're going to see. We can combine sorting algorithms. Basically, we want to take the benefit from each sorting algorithm by looking at how each sorting algorithm is good on its own. Okay, let's say, for example, let's have a quick review of something that you already have seen in the midterm, I guess. So if we have an algorithm which is 1000 n log n, and another one b, which is n squared. You cannot see that. So we have algorithm A1, which is 1000 n log n, and algorithm 2, which is n squared. Now, if n is 10, what is the runtime, the number of runtime steps here? Okay, let's make it something easy. 16, 2 to the 4. So that would be 1000 times 16 times 4, and that's going to be something like that, 64,000. And here it's going to be 16 times 16, which is 2 to the 8, which looks like 512 over 2, which is like 256. So this is a square, this is a quadratic algorithm, and this is a log linear algorithm. Quadratic, in the worst case, obviously in the infinity, is more expensive than the log linear algorithm. Okay. However, when the values of n are small, then this log linear algorithm, this quadratic is better. Do you agree? And we said that this is because of this. What do we call that? Yeah, the constant factor is high for the log linear algorithm. So, based on this, we are going to observe the following. Insertion sort is big of n squared, but has a low constant factor. However, for example, quicksort that we said is the best of all. Quicksort, which is randomized and in place, is n log n with a higher probability, but has a higher constant factor. It's not as high as merge sort, but it's a higher constant factor than insertion sort. So we can imagine that insertion sort is something like 10n squared, and quicksort is something like, I don't know, 1000 n log n. I mean, it could be the case. These numbers are going to depend on the implementation. Okay? But for sure, when n is small means in some textbooks less than 30, but this is not like engraved in stone. Okay? When n is small, insertion sort has a low constant factor compared to quicksort. So when n is small, insertion sort is better to use than quicksort. So if I give you a sequence which is like less than 30, it's better to use insertion sort to sort the sequence than use quicksort to sort the sequence, because although it is quadratic, although insertion sort is quadratic, it has a lower constant factor, and hence for this value of n is going to have a smaller number of runtime steps. Okay, so if the input is small enough, then we can use insertion sort because it has a low constant factor. So we are going to use this observation to enhance quicksort. So quicksort, as we know, takes a sequence to sort, partition A into A1, A2, A3, and then does what? So that's quicksort, and then recursively calls itself over partition A1 and partition which partition? A3, and then glues together this result with A2 with this result, okay? And then puts them together. Now we are going to change this sorting algorithm so that instead of quick sorting A1, we are going to check, okay? We are going to check if the sequence is less than 30, if the size of the sequence is less than 30, we are going to use insertion sort. We're not going to use quicksort. Okay, so we have a sequence. Let's say size 1000. We apply quicksort to it. That's going to give us, for example, let's say randomized quicksort is going to give us something like 500 over here and about 500 over here. And then we keep doing that, 250, 125, 60, 4, or something, 62, and then 31. Now, when we reach 31, we are not going to use quicksort, we are going to use insertion sort. Okay, because it's small and insertion sort should be faster. Okay, so the new algorithm is going to look like quicksort of A if size of A is less than or equal, for example, 30, then insertion sort A. Else partition into A1, A2, A3, and quicksort A1 and quicksort A3. Okay. When we call quicksort A1, obviously, because it's the same function, we are going to check if the sequence is less than 30. If it's less than 30, then we are going to insertion sort the sequence. So this is how we combine insertion sort with merge sort. We keep track of the size of the sequence, which is easy. We just check. If it's already too small, we can use insertion sort instead of quicksort. This is what I'm saying in the slide here. About constant factors, about n0, which is the value we're going to check. Reportedly is less than or equal to 30, but that's not always the case. I think I asked you in the practical to derive the value. I'm not sure. Or maybe I ask you here. Okay, I ask you here. In this question, I'm saying try to combine the algorithm that you have done in the practical, the quicksort with insertion sort, and find out what is the value of n0 which is going to give you better performance. So you can choose, for example, n0 to be 30. So in the algorithm, when you say if size of array is less than, for example, try is less than 30, then do that. Compare the performance of quicksort in this new code with the old performance. Do a few runs, and if there is some performance gain, try to increase the value or decrease it. I mean, do your experimentation so that you know what is the value where using insertion sort is better. For example, if you choose n0 to be 1000, you get perhaps a loss in performance because using insertion sort on a sequence of 1000, knowing it is a quadratic algorithm, that's going to make things worse. Now, 1000, if it's bad, okay, try 100. If it's bad, try 50. If it's good, go back to 75 and try to find what is the value of n0. This is for your own good. I'm not requiring you to do that. This is for your own good so that you understand better this issue of merging sorting algorithms, how you test them, etc. Okay, so that's an exercise for you if you want to do it. Now, we have seen 4 sorting algorithms, 2 which are quadratic, 1 which is log linear, and 1 which can be log linear if you use the median of median algorithms, or is log linear in the with high probability using just randomization techniques. Now, there are other sorting algorithms. There is heap sort that we're going to see in a lecture future if we manage it. Bubble sort, which is another quadratic algorithm. It's the most famous sorting algorithm, but there's no point in teaching you this sorting algorithm. It's not efficient at all. There's nothing nice about it. Tournament sort, shell sort, and these are all comparison-based sorting algorithms. There are other sorting algorithms which are not comparison-based. You have bucket sort, for example, counting. These are all non-comparison based sorting algorithms, which means they do not obey the lower bound performance n log n. You can find big O of n of these, but they are non-comparison based, which means they cannot be used in the general case. For example, some of them require that the sequence only contain elements of 3 different types. So the elements can either be blue, black, or white. The elements can either be the number 3 or the number 7 or the number 11. So they require the sequence to be in a specific shape to have a better than n log n performance. Okay, so they are only specific in certain cases, a better than n log n performance. Okay, so they are only specific in certain cases. They're not general, because the general sorting algorithm must be comparison based. We need to be able to compare everything to everything else. Okay, we need to be able to compare. Once we need to be able to compare, there is no escaping n log n performance, n log n lower bound on performance. Okay, and then how do we choose the sorting algorithm? So we have seen a case, for example, insertion sort. If the sequence is small, we use insertion sort. If we don't have much memory in the computer, then we cannot really use something like merge sort, which requires extra space. If we have multiple processors and we can parallelize our sorting algorithm, then we basically, every recursive call, we make it on a new processor. So when we partition into A1 and A1 and A2 are not executed in sequence, because right now they are executed in sequence. We have to call A1 and recursively divide it, and then call A2 and recursively divide it. So it's not like we are drawing. They're not happening at the same time when you have one CPU. So if we can parallelize that into many CPUs, so everything can happen at the same time, and this gives us a huge boost. So this is applicable only to quicksort and merge sort, because they are divide and conquer, and they can be parallelized. However, sorting algorithms like insertion and selection sort, it's not that obvious how to parallelize them. So depending on the context, but in general, if you have like big sequence, which is the most or the only interesting kind of sequence, you better use quicksort, because reportedly it's the better empirically, of course, not in theory. Okay, empirically, randomized in place quicksort is the best sorting algorithm around. Okay, I think we're done with sorting. Now, have you been able to print the slides or to look at the slides? Because yesterday I've received the comments that people were not able to access lecture 5 slides. Were you able to? Were you bothered to? Okay. Do you anybody has the slides? Do you usually have the slides? Right. I don't know what's happening with Google, but certainly it's not my problem, it's Google. Lots of people were complaining yesterday. So I need to take like a 5-minute break while this thing stops.